Dear colleagues, welcome to the next AI seminar at TI. And today we are happy to have Professor Kun Zhang from MVGUI. And Professor Kun is a world-leading expert in causal inference and in machine learning in general. And we are very happy to have him here and to listen and to know about his latest research and generally about the topic, which is very modern and deserves a lot of attention, obviously. Thank you.
Thank you very much, Maxim, for the invitation and for the introduction. So, hello, good afternoon, everyone. So, as you can see from the title, this talk is about the methodological advances in causal representation learning. I'm going to talk about why we have to use the causality in a lot of scenarios, and then after that, I will talk about how we can discover causality, right, which might be causal structure or hidden variables with the causal relation and so on. And I also briefly mention some machine learning problems like domain adaptation or transfer learning as examples, as applications of the learned representation. So if you have any questions, please just let me know during the talk. It worked now, okay. Okay, good. So first of all, we know that, let me start with a couple of examples to illustrate the difference between correlation, dependence, and causality, right? You can see why we care about it. So this is a famous example used by Fisher a long time ago. So basically, you can see here, we know that this is the underlying picture. In order to change the incidence of lung cancer or lung disease, we cannot just rely on dependence. Clearly, we want to find the causes, right? We have to change the cause in order to make sure something will happen. That's very clear. Good. So here, this is the example, real-world data set. I don't know why you cannot see it clearly. Okay. So here is a real data set published in the 1970s. Now you can see something interesting. So basically, this is a data set of kidney stone patients. So we have two group patients. One of them has small stones and the other has large stones. And we have two treatments, A and B. Now you can see for each of them, right? Treatment A is better, as you can see from the higher recovery rate, right? A is better. However, if you put the data together on the whole data set, you can see that B seems to be better because recovery rate is 83% versus 78% for treatment A. Now comes the question, suppose you are a doctor and suppose you only care about the recovery rate. Now a new patient just comes. Would you recommend A or B? A, right? Would you like to recommend B? So some people say, oh, see here, B is better, right? Why not just recommend B? Because that's why it's known as the paradox. Now we know why. Basically, here in this problem, we care about only the information of the causal influence from treatment on recovery. That's all. We don't care about dependence. The dependence can be very different from causal influence because of the common causes, right? Some other common causes. So the dependence can be almost arbitrary, but whenever we make recommendations, we care about the causal effect. Specifically, we care about this causal effect, and if you really care about this one, you fix the stone size, then clearly A is better. And similarly, here we have another problem, another kind of illustration. Here you can see the scatter plot of exercise and collateral. If you know the age group, it's good. The more exercise you do, the less collateral you are going to have on average. That's good. So we should do more exercise. But if you put the data together, now you can see clearly the correlation is positive. Then the conclusion is that, oh, the more exercise you see, the more collateral you see, right? So in this case, you can see we cannot rely on dependence picture or dependence pattern. We have to figure out the underlying causal process and make use of it whenever you make a recommendation. Okay, so this is known as Simpson paradox. With causality, we know we can solve the problem. The last example is about some kind of strange dependence in the data. So if you go 50 years back in the States, you'd find that the female students were kind of smarter than male students on average. Why? We believe that kind of females and males are almost equally smart in the whole population. Basically, this is another problem known as selection. So at this moment, both gender and IQ were kind of causes of being admitted to college. As a consequence, although they were independent, given the consequence, they will become dependent, right? You can think of this guy as X, this one Y, this X plus Y, right? Is a consequence. Given X plus Y, clear X and Y will be perfectly related. So you can see they are clearly related. So we have to be very careful when we deal with this kind of data. So basically, all kinds of data collected on internet have this issue. It's known as selection bias. So another example is known as kind of survivorship bias example. Here you can see the damage to the aircrafts came back from wars. And this is the true story in World War II. So you can see, now suppose you want to increase the chance for the aircraft to safely come back. You want to put the armor somewhere, right? So would you put the armor here or here, right? Now you can see to answer this question, first of all, the military gave a wrong answer, and then statistician world gave a correct answer. So he said, we should put the armor in those areas, right? That do not really suffer from the damage. Why? Because in order to answer this question, first of all, we have to come up with a story. If we don't have a causal story, then we don't have an answer. And different causal stories can give you different answers. Specifically here, being hit and where it's hit are causes of, say, survival. And then we only observe data points correspond to survival, say, equal to 1, because they survived. And then we want to infer something about the aircrafts that fail to come back. And then we want to make a difference, right? So in order to infer the information of the aircrafts that fail to come back, we have to assume, or we have to make use of some domain knowledge. Now you can see, in order to answer a lot of questions, we have to rely on not only the data, but also the underlying process, right? Okay. This character back explained my experience, right? A long time ago, I intended to think that correlation implied causation, and then after taking some classes, I realized it was wrong. But after doing research in the field for kind of very long, now basically we can say that in almost all situations, we can discover causality from data. What's the difference between association or dependence and causality, right? This is the definition of causality in terms of intervention, so do it intervention. So basically, if you do intervention on X and find a change or difference in the distribution Y, then we say X causes Y. Of course, you may want to see the definition of intervention, right? So when you do intervention on variable, basically you can only change this variable directly, but not any other variable in the system. So this is the way. Otherwise, if you change multiple variables, you may say, oh, see, in order to change X, or after I change X, I see a difference in Y, right? But actually, you may directly change Y. So you have to get rid of that possibility. Every time you only change one variable directly. And then if something else happens, you know, oh, they are the causal link from the guy you intervene on to the target variable. Okay, this is intervention. Clearly, the definition of intervention is very kind of, is very good, but it's very hard to make sure that it's intervention, because without understanding the connections among those variables, how can I make sure that this action changed only this variable directly? I don't know it, right? Because I don't see the connections. So that's why I would say the definition of causality in terms of intervention could be circular. If you know how to do intervention, you actually know causality. If you know causality, you know how to do intervention. But the circular definition could still be very useful. The key point is how to introduce appropriate assumptions so that we can enter the world of intervention and causality. Okay, so to make the difference even clearer, suppose XY dependent, right? In statistics, you may use conditional distribution or joint distribution dependent pattern to explain their dependence. But even with almost the same dependent pattern, you may have different causal structure. So here you can see different causal structure clearly give us different answers to the causal question. Here you want to see the effect of X on Y. So you do intervention X, and then you want to see the distribution Y, right? So you can see clearly across the three scenarios, the answer could be totally different. That's for sure. Now, I gave some stories or examples to illustrate why causality is essential. Clearly, if you want to make difference, or if you want to treat a disease, you care about the causality. But even in ML, even in machine learning and AI, generally speaking, we care about the causality. For instance, if you want to do transfer learning, domain adaptation, where you train something from here and apply it here, clearly you care about how the distribution changes. You have to be adept. You have to be to adapt to the new environment in a good way. So you have to realize or understand what changes, right? And here, for AI diagnosis system, we care about not only the result, but also why, right? Why did you say, oh, this guy has this disease? And you also want to go further. You want to see how to change it, how to find a good treatment for the disease. For recommended systems, the same thing happens. If someone recommended something to you, right, you ask why. Why was this item recommended? Right? What's the purpose and so on? So care about causality. Here you can see a kind of very famous example. The panda, if you add noise a particular pattern or change particular pixels in specific ways, then the machines will say something different, right? So this is horrible. How can we avoid this problem? So mathematically, you can prove the following thing. If machines learn and make use of different set of high-level representations, right, from the raw input, then they will always suffer from the adversarial attack problem, because you can always tune the input, raw input, so that either machines or human beings learn a different set of high-level representations, right? In other words, in order to avoid this problem, we have to find a way so that machines can, representations, feature representations that machines can learn and make use of are consistent with what we have, what we use, right? If that's the case, then it's good. So basically, we make a decision based on the feature representations, right? Machines do the same thing, and the feature representations are actually consistent. Then we don't have this issue anymore. Now, next question is, what kind of feature representations do we use, right? So roughly speaking, we use causal features or generative features. The next one. Why do we learn causality, or why do we learn causal representation? First of all, a lot of people say, oh, that can benefit downstream tasks. Yeah, usually it's the answer is yes, and people actually gave a lot of evidence. And some people say, oh, we want to answer why questions, we want to do intervention. Good. And some other people say, we want to recover the property of the true process. Good. And even if you don't believe that's the case, right? In situations where you don't have to do interventions, a philosophical way to argue why we have to use causal representation that follows, as one way, right, was given by Kant. So we only have access to this world of experience, right? We just have access to the world of experience. The world of experience was produced by world in itself, the true world, right? We don't really have, we don't have direct access to. And the pure form of experience basically is about our perception system. So whenever we perceive something, we automatically apply those things like filters. And right in this world, in this system, we have space, a concept of space, a concept of time, a concept of causal order, and so on. So whenever we perceive something, you can see the kind of footprint of causality, space, time, and so on. So that means in order to make sure machines are consistent with us, we have to make sure the machines can understand this world. So they know, oh, in this world, the causality is built in, right? So that's why we have to find a principal way so that the machines can learn and make use of the causal representation from data in order to communicate seamlessly with human beings. Now, the second question is how we can learn causality, right? So clearly, that's the important problem. In order to answer this question, we have to see two things. First, in the data, we can only have access to the data, right? So what kind of information of causality or what kind of footprint of causality can we discover in the data, right? So we have to figure out the footprint of causality in the data. And then, given that, we want to establish the so-called identifiability. We want to say, oh, yes, under that, some assumptions, I can really uniquely recover the underlying structure or the underlying quantities with guarantees. By guarantees, I mean, you can show that this is the only solution. This is the unique solution, right? Okay, now let me just address those issues one by one. First of all, when we use causality, essentially we just care about one property of the causal system, known as modularity property. So here you can see we have a causal system, right, consisting of rain, wet ground, slippery, and so on. When we say it's causal, we mean the following thing: the whole system can be decomposed into a lot of irrelevant modules. One module generates one variable from its parents, and although all the variables can be dependent, those the modules are not relevant to each other at all. They are separate modules. There are no relationship between modules. You can change one without changing any other. If they change independently. So this is modularity. Okay, this is the high level of independence. It's not about independence between variables. It's not about just conditional independence. It's a high level independence, process independence. Basically, here you can see no matter how you make it rain, the mapping from rain to wet ground would be the same or would not be changed by that, right? Similarly, no matter how you make the ground wet, the mapping from wet ground to slippery would be the same, right? So this is modularity. From this property, we can immediately see some information of data produced by the causal system. First of all, if you fix this guy, if you see the same value of x, then in order to predict y, you don't care about z, right? Because this system and that system are not related. Good. The change here will not influence anything here, as long as x is given. So this is the conditional independence. Okay, the first property is the conditional independence. Later, you can see how we can make use of conditional independence to recover causality. Second, now you can see no matter how you generate x, the error in this system, right, is not relevant to that at all. In other words, if there are no common cause or direct hidden common cause, then the error in y would be independent from the parents of y. X and e are independent, and this is known as independent noise condition. Okay, we can see how we can make use of this condition to find the causality. And furthermore, if the system changes, for instance, right, if you travel across different places, they can see the probability of rain could be very different, right? The system could change. However, you can see the causal system will enjoy a minimal changing property. So if this guy changes, right, this guy may not change, this guy may not change, right? In the causal system, you have only one change, one module changes. But if you have a wrong representation, you have to suffer more changes. Multiple modules will change if you have a if you don't have a causal system. And furthermore, if they change independently, right? Because there are no common cause for them. The modules are not related, so they change independently. We call this property minimal and independent changes. Later you can see we can also make use of such properties to directly recover causality. Here by causal discovery, I mean the task of recovering the underlying causal structure from data. Recently in machine learning, a lot of people talk about causal representation learning. Essentially, you can consider causal representation learning as a subtask of causal discovery. So in causal representation learning, you care more about the high-level hidden variables, right? Given images, clearly we cannot say, oh, the image pixels are causally related. You may want to say that, oh, they were generated by some high-level latent variables like concepts, right? So you want to recover those latent variables and their relations, probably layer by layer. So this is basically a causal representation problem. Now let's see how we can solve the problem. First of all, regarding the problem, let's look at the setting of the problem. So essentially, there are three axes or three dimensions of the problem. The first one is what kind of data do you have, right? In some cases, we have i.i.d. data. You have data generated from a single distribution. In many cases, that's the case. And in some cases, you have non-i.i.d. data. You have time series data, or you have data with a distribution shift, and so on. This is the first dimension regarding data. The second one is whether you have a prior information about the causal influence. So in some cases, when I say, oh, the system should be very close to linear, right? So the second dimension is whether you can benefit from parametric constraints on the causal influence. The last one is whether you allow latent confounders in the system. Here by confounder, I mean a direct common cause of at least two variables, right? And by latent confounder, I mean a direct common cause of at least two variables in the system that you don't measure, right? So the latent confounder. Now let's see how we can solve the problem. Basically here, you can see a summary of the current results of state of art. In the i.i.d. case, most of the time we can just recover equivalence class, some kind of equivalence class. And under some further assumptions with parametric constraints, you can even have unique identifiability in many cases, and so on. And what's more interesting is to look at the non-i.i.d. settings. And here, in many cases, you can see we can discover the underlying process uniquely. I will give examples. So let's go with this example. So this is the basic data set in archaeology collected by my collaborator, Marley Nobeck. So I really like her last name, Nobeck. Just go forward. She collected 250 skeletons and she measured 8 variables. In archaeology, they really want to understand why people in different areas look different, right? So what's the cause? How are those features related? So that's why they collect the data. And then clearly from the data, we have no idea. We cannot do intervention. right? Even if you can do the invention, say, you can just force some people to move to a particular area. You have to wait very long to see the consequence. So in this case, we have no choice but to analyze the data to see the causal relations. We applied conditional independent Bayesian method or constraint Bayesian method. Here you can see the workflow. Conditional independence is one type of the kind of footprint of a causal system, right? A modularity property in the causal in the data. So now let's see how we can make use of conditional independence to recover the information of causality. We start with data. From data, we can discover a set of independence or conditional independent relations right here. And then you can show the following thing under some assumptions, including faithfulness assumption. I will explain it later. Then you can recover the causal structure. Why? Because you can show that two variables are adjacent if and only if they are always conditionally dependent, no matter what you condition on. That's it. Okay. So they are always conditionally dependent, no matter what you condition on. Then they are the edge in between. Here, by faithfulness, I mean, basically faithfulness is a kind of popular assumption for the constraint-based method or conditional independent-based methods. It says the following thing: in the graph, you have deseparation, right? And in the data, you have conditional independence. Essentially, there's no fake or actual conditional independent relationship in the data compared to deseparation relations. That means whenever you see conditional independence in the data, it's a reflection of the property of the graph. Okay, that's faithfulness. That's why it's kind of they are faithful to each other. Now you have this set of constraints, independent constraints. You want to find a graph or set of graphs to satisfy those constraints. Actually, whenever they are conditionally independent, you can remove the edge. And then after that, you have a skeleton. And then in this case, you can see the following thing: x2 and x4 are independent given x1 without the condition of x3. Then this is the only possibility. This is known as the weight structure. So x2 and x4 must be causes of x3. Why? Because if you change any direction here, then without the condition of x3, you cannot make them conditionally independent because they are the way for them to communicate with each other, right? Either this way or that way or this way. You have to condition this guy in order to make them conditionally independent. But now that's not the case. Then the directions must go this way. So this is this structure. And furthermore, direction must go this way because otherwise, if the direction goes this way, it's a V structure, right? V structure, two guys pointing to middle guy. But we know it's not the case because x2 and x5 are conditionally independent given this guy. So that's not the case. Now you can see in this case, we end up with this result. It's good. We can discover some information. But you may have questions. First of all, can we allow latent confounders? Right? In the world, there are so many variables. How can you say that, oh, I can assume there are no confounder? So that's the first question. The second one is that here you can see for some edges, we don't have directions. How can we find the directions? Now let's see how we can address those issues. First of all, here you can see the result on the data I just mentioned. Geodistance influences climate. Climate influences cranial size, cranial shape differentiation, and so on. Gender also influences the cranial size. So you can discover such relations just from data. Okay. Now let me give 2 examples to illustrate the following thing. Even with only conditional independence relations, in some situations, you can really say something about the latent confounder. So this is very cool because you make use of very weak information, but you can say something about the whole world by analyzing only few variables, right? In the first example, we have 4 variables, x1, 2, 3, 4. Suppose here, right, you can see the set of independent relations. Now, if you apply PC, you can get this. Oh, x1, 2 independent, right? Right there, they're independent. So, and 1, 2 are independent without condition on 3. So we have a V structure, and so we do orientation propagation. We get this result. Good. This is the result by PC. Now the question is whether it is possible at all for x3 and x4 to have a latent confounder in between. Do you think in the whole world, there could be such a C variable as a common cause of x3 and x4? What do you think? So it turns out that it's definitely not possible. Why? Because if you have such a C variable, right, then x1 and x4 will not be deseparated given 3 because of this path, right? Now we know they are condition independent. We know clearly there cannot be such a C variable. So that's good. In this case, you can see we are completely sure that X3 is the cause of X4 and that there are no compounder for them. There are no latent common cause for them. It's cool because you just analyze a very few variables and you can say something about the whole universe. No matter how many variables you collect, none of them can be a common cause of X3 and X4. And you are completely sure about the causal influence from 3 to 4. And you can use this idea to solve a lot of problems, right? You can in our everyday life, we can observe or we can try to judge conditional independent relations, and then we can just make use of this idea, and we can say, oh, wet ground must be a direct cause of slippery without the compounder. We can do that. Okay, is the first example. Second example, we have another set of independent relations among the variables, and then the question is whether it is possible for 2 and 4 are compounded. So the answer is in this case, X2 and X4 must be compounded. They must be compounded. Although they are dependent, they are always dependent. X2 and X4 are dependent. We know that there are no direct causal influence between them. Neither of them is the cause of the other, and their dependence is caused by some latent compounders. And you can also see a lot of applications of this idea. For instance, let X1 be I'm not sick, or whether I'm sick. X2 be whether I'm in this lecture room. X4 be whether you are here, and X3 be whether you are sick, right? So you can easily verify kind of conditional independent relations, and they can say that although X2 and X4 are dependent, there are no direct causal relationship between X2 and X4. Instead, they're the common cause. So we have this similar here, right? That's the cause. So we can really make use of the idea to infer the information of the underlying process by analyzing the statistical properties of the data. Okay, any questions?
Now, probably set of X, for example, in this example, and we can we only for like for a pair say well there is this latent compounder or not, or we can say it for the whole set of variables, like for any pairs.
Oh,
they're like very fundamentally given this independence relation to reconstruct this for all pairs.
Okay, the question is yeah, now you can see the for some pairs, we can see whether they are compounded and whether they are the direct causal influence in between, right? And your question is whether we can say the same thing for each pair. Okay, that's excellent. The answer is unfortunately no. Otherwise, it's too good to be true, right? So you can just solve the problem, every single problem. No, only in some situations you can have very, very informative answers. So basically, this is the part of FCI, fast causal inference method developed by Peter Spertis. Peter Spertis is the creator of the field of causal discovery, my senior colleague at CMU. Basically, FCI has been proven to be correct. The result is correct asymptotically under the faithfulness assumption. But as you always allow compounders, right? Allow latent variables. As the price you have to pay, usually the result may not be very informative. For instance, you may say, oh, here you may have compounders, right? Or maybe there are no compounder. I don't know, right? But for some pairs, you can have very informative answers with only conditional independent relations. Is that answer to your question? Only for some pairs. Yeah.
In this example, you demonstrate, so for example, in example 1, there is only, we can say only about extremes 4, there is no L. And we cannot say about any other.
Yeah, to the right. We cannot say but between for X1, X3, right? There could be a compounder. Then you have the same set of conditional independent relations. For instance, there could be a kind of C variable as a common cause for X1, X3. We don't know.
How do we can, like, say, find all pairs for which we can definitely say something, and how to find all pairs for which we cannot say?
Exactly. So this is the part of FCI algorithm. So this guy can detect all those pairs, right, for which you can say whether they are compounders, right? You have a yes/no answer. Good. Okay. Cool. Actually, now we can go further. You can see I can give another answer. Then for each pair, we can say something in 1 minute. Yeah.
In this like specific algorithm to have this conditional independence, how can you measure like your certain in the sense that there might be what you call like unobserved or hidden compounders that you can't see on your scheme, but they're there and you're not measuring anyhow.
Wonderful. I will go basically I will talk about this in 5 minutes. Wonderful. So here we just try to see the causal relations among the measured variables. Even if we say, oh, they are compounded. Actually, we do not really care about the relation among the compounders, right? And in FCI, actually, you assume the compounders are independent. In many cases, if you care about the compounders, right, like in image scenario, it doesn't make sense. It doesn't make sense at all because the compounder can be related. So we'll come back to this problem in just a few minutes. Good. Yeah. Now let's go further. For each pair, what can we do? So here, if you are willing to assume something, then all of a sudden, just for each pair, you can say, oh, whether they are compounded and whether X causes Y by making use of functional causal models. Zoom is kind of very greedy. So here, now we can see we are still talking about the i.i.d. data. Now we make assumptions. In the previous method, we didn't make any parametric constraints. But now we just assume some parametric constraints on the causal inference. And for now, just for the moment, we assume there's no latent compounder. And then you can immediately find the causal direction. Why? Here's the illustration. So X generates Y. This way, the noise is independent from X. Good. So if you try to explain why the effect with X by doing say linear regression, you can see you recover the true noise. The true noise is independent from X. That's good, right? But if you do the same thing in the reverse direction, you can see that the residual is, of course, uncorrelated from the predictor, from Y, by construction of linear regression, but clearly they are dependent. So the message is that in very general situations, if you are willing to assume something about the functional form of causal influence, then you can determine causal direction. The same thing happened to the post-nonlinear model, which I will briefly talk about, and the additive node model, and so on. Basically, in all those cases, you may make very, very weak assumptions, right, about how X influences Y, the cause influences the effect. But you can show that in the reverse direction or in the wrong direction, the error term cannot be independent from the predictor. So let's have a look at this post-nonlinear model because it's very general, right? If both nonlinear functions are linear, then it's a linear model. If this guy is linear, then it's the additive node model. And you can see when the noise is multiplicative, it's a special case. So it's rather general. But even for this model, we can still establish the identifiability. So here you can see some empirical results. We have only data points right here, only the data points. So from data points, we fit the model in two directions. And then you can see when you assume X1 causes X2, you estimate the error, you estimate nonlinear function, you estimate error, they are independent. But in the reverse direction, or in the alternative direction, the estimated error cannot be independent from the hypothetical cause, as you can see from here. Then we can say, oh, we should prefer the direction from X1 to X2. Actually, they are the altitude and the precipitation of kind of 300 cities in the world. So clearly, altitude causes the precipitation, not the other way around, right? Theory. Basically, you can give some theoretical guarantee. You can show the following thing. If the data was generated by this kind of very general model, post-nonlinear model, very general model, then only in 5 specific situations, you can find, you find an independent error in the wrong direction as well. Only in 5 situations, they are symmetric. Because if they're kind of not one of those situations, then only in the correct direction can you find the independent error term. Those 5 situations are very specific. The first one is the linear Gaussian case. So for causal influences are linear and the distributions are basically just generally Gaussian. Essentially, all of them are very specific. You have to tune the parameters of the nonlinear functions and the distribution very carefully so that one of them holds true. In other words, generally speaking, even for the data generated by this very flexible model, you can find the causal direction. And furthermore, you can determine where they're the compounder because you can easily show that if there are latent compounders for X1 and X2, then you cannot find an independent error. Okay, so if you are willing to assume something, you can, for each pair of the variables, you can say whether they are compounded and whether X causes Y or Y causes X.
For this statement, with the five specific cases. So is it the statement only for scalar, like when X and Y are scalar, or for
wonderful? Yeah. So basically, this is for kind of separate universe variables, scalar variables. However, you can easily extend the result to a system with arbitrary number of variables. Why? Because in causality, basically two-variable relationship is essential, is fundamental. Why? Suppose you have X, Y, Z, right? Now you have three variables. And actually, suppose X causes Y, causing, can I just draw something here? Then you can see Y. You can immediately solve the problem by making use of this result. So suppose X, suppose this is the case. Now you have three variables, right? However, you can always transform the problem to the two-variable case. If you consider conditional distribution Y, Z, given X, meaning that you fix the value of X, right? You consider the same value of X, then this is a two-variable problem. You can determine direction and you can determine whether they are compounded. That's why if you solve the problem with two variables, in theory, you can solve the problem for an arbitrary number of variables. Good? Okay, good. Now, as promised 5 minutes ago, let's see how we can talk about how we can discover latent compounders. So let me give you the motivating example. So in psychometric studies, very oftentimes we have answer scores to the questionnaires, right? And we clearly the answer scores to different questions are related, are dependent. But we don't believe that they are directly causally related. Instead, we try to analyze the answer scores to infer the underlying hidden meaningful mental conditions. And the mental conditions could be related. As you can see from here, we analyze those measured variables xi's, and we try to recover those hidden variables li, right, together with their relations. This is what I mean by latent causal representation learning, or just causal representation learning. You want to learn the representation, and you want to see how those things, hidden variables, are related. We propose a set of methods to solve this problem. So they are kind of slightly technical. That's why I will not talk about the methods, but let me just give some applications. So this is one application. We analyze the teacher's burnout data with 28 variables and 500 data points. So here, basically, this is a hypothesized model produced by experts. We analyze the data with our generalized independent noise condition. So basically, GIM method, generalized independent noise condition based method. We recovered basically almost exactly the same result. We discovered all those hidden variables right here, and we discovered their causal relations. So this verifies two things. First of all, this kind of hypothesized model given by the experts is very good because they didn't rely, the experts didn't rely on data. They just make use of domanology. And we just make use of data without touching the domanology at all. We produce the same result, right? So computational methods are very useful in order to recover this kind of representation. Okay, so now you can go further. So recently we try to infer deep structure, basically consisting of a lot of latent variables by analyzing all of those kind of measured variables, xi's. Turns out that it's not a really difficult problem, so we can solve the problem. We can refer to the recent papers. Here you can see the latent variables may have other latent variables as children. This is very different. In the previous setting, we assume that each latent variable has some measured variables as children, right? But now you can make it very completely general, as you can see from here. So under some assumptions, the whole structure is completely recoverable, including the relations among the latent variables. So essentially, you have a way to recover the deep structure. This also explains why deep learning is really useful, because if you have a way to identify the underlying deep structure, what does that mean? It means this structure must have some unique property, right? Actually, here in some other way, this structure enjoys some kind of sparsity. You may have a lot of latent variables, but the total number of contiguous freedom is actually minimized with this structure. Similarly, here, this work is completely theoretical. So we gave the necessary and sufficient conditions. How can I just get rid of the Zoom Zoom part.
Yeah.
Very good.
Okay, it's over there.
This part still there, but maybe okay. Let it be. Okay, so here in this work, we just produce the necessary and sufficient conditions of the structure involving latent variables so that it's identifiable from data. That's cool because here you can see a list of all causal graphs involving latent variables. Here involving, you cannot see the color, I know it's too bright. In which we have only 3 measured variables, right? And all of them are identifiable from the measured variables. The latent variable can be causes, direct cause of measured variables, or there can be effects of the measured variables and so on. It's completely flexible, but given any graph, you can apply the condition, you can see whether it can be recovered from data. Okay, so now let's go to the next part. Previously, I was talking about the i.i.d. case. You have a single distribution, right? Essentially, you make use of some kind of properties produced by modularity property. Sometimes you prefer simple model, and you can show that, oh, with this specific condition, I can recover the underlying structure uniquely, right? Now we have non-i.i.d. data. What can we do? I think because maybe it's too slow. Give me 1 second. Okay, I will try to, for this part, let me go very fast. So,
structure doesn't change, but some marginal distribution changes. So what's so
wonderful, wonderful. All those situations are covered. Yes, all situations are covered. So you can have changes in the causal influence. You can have changes in the marginal distribution of the cause, and so on. All of them are just instantiations of non-stationarity. Okay, that answers your question. And here by non-i.i.d., basically there are 2 possibilities. You can consider non-i but i.i.d. data, right? It's basically they're not independent, but they have the same distribution. Essentially, you have a stationary time series. Or you have I but non-i.i.d. data. So you have independent but non-identically distributed data. You don't have time delayed causal relations, but the distribution can change. Okay, so let's see how we can handle those problems. First of all, if you have stationary time series, under some very strong assumptions, you can just use a kind of classical method to recover causality, like a gradient causality, right? You have nonlinear, even non-parametric version of gradient causality, essentially the conditional independent relations together with the temporal constraints. Causes should be earlier, should happen earlier than effects. Okay, but the assumptions are very strong, and you don't allow instantaneous relations. If the resolution of data is very low, clearly you have to find a way to explain why the data dependent instantaneously. So there was some work on how you to extend the model to incorporate the instantaneous relations. Okay, good, but basically it's rather classical. Let's go further. Here's the problem setting. So we have high dimensional time series, right? Like video data. We assume that the video data are just invertible nonlinear arbitrary, nonlinear transformation of the meaningful underlying latent processes, Zi variables. So we have latent processes. In video data, you can think of those things as the underlying objects, right? And so on. The latent processes can be causally related. One object can influence another object with some time delay. So Zi variables processes are meaningful, right? And they could have a causal relation in between, but the causal influences should be time delayed. There should be some time delay. If the resolution is high enough, then this assumption would hold true, because we believe that it takes time for causal influences to take place, right? Okay, then under very weak assumptions, you can recover those latent variables without any difficulty. So we can even allow completely non-parametric models for the relations among the latent variables, latent processes, and you can even allow complete non-parametric models for the mixing function to generate the time series from the underlying concepts or underlying latent processes. Good. Now let me just give some illustrations. So here, let me just show the results on 2 very simple computer vision data sets. The first one is known as the kitty mask data. Here you just have the video, right? You have the raw video as input, and we recover 3 processes. It turns out that the 3 latent processes, recovered processes, are not related to each other. and they are kind of movement in one direction, movement in the orthogonal direction, and the size of the mask. Very simple. You can recover those things automatically. This is the second data set. It's known as mass spring video data set. Here you can see a video of five balls in different colors, and between some pairs of the balls, they are kind of there's a hidden spring. That's why they are related. So for some pairs of the balls, they are related. And then we just use the raw video data as input, and we recover 10 variables, 10 processes. It turns out that they are just the XY coordinates of the 5 balls. And this is the causal graph. Over those recovered 10 variables, 10 processes. So now you can see from the video, you just perfectly recover the XY coordinates of each ball together with their relations. So this is very helpful if you would like to do video understanding. It's a kind of completely unsupervised, right? But you can really recover the underlying meaningful representation and their relations. Okay, good. So now let me go further. How can we handle independent but non-identically distributed data? We have non-station data almost everywhere, right? In some situations, we have a time series, but if the value of the background variable changes over time, then we have non-station data. So that's basically this happens to the brain signals, right? As time goes on, you can see the brain signals may have different distributions. If you collect data under different conditions, you can have different distributions, right? Because different conditions can generate different distributions. So this is another kind of heterogeneity. So you allow, in other words, you allow a causal relation to change as time goes on, or as you go from one condition to another. So there's some causal relation that can be stronger, right? Some distribution can change, and some causal relation can be weaker, and some of them can even disappear. Okay, so this is non-stationarity. From a causal perspective, if you have non-station data, there must be some change in the causal process, right? Because the process generates distribution. You can have a change in the marginal distribution, you can have a change in the conditional, and so on. And here, actually, it's easier to recover causality. Why? Because causal modeling and the distribution shift are heavily coupled. At the beginning, I explained the property of modularity, right? So it implies that if you have a causal system, and if you have a decomposition of the Jordan distribution according to the causal system, then you have minimal changing property, and you have independent changing property, right? Now, from non-station data, you can observe, you can analyze how the distribution changes. You can try to verify those conditions in order to recover a causal representation. Okay, so now let's see how we can proceed. So this is the first line of research. You are given variables under some assumptions. You want to recover their causal relations. Also, you want to see for which variables the causal mechanism actually changes, either over time or across different conditions. Okay. So we propose a method to do so. First of all, you can determine for which variables the causal mechanism changes. Now this is very good because it's not just about the change in the Jordan distribution. You know the change right here. When we say the causal mechanism for V2 changes, we mean the following thing: the influence from the parents of V2 on V2 changes. It's very local and modular. And then we can find the skeleton, causal skeleton, and then we can find the direction. And when you try to find the direction, you also benefit from independent changing property because the modules should change independently. And we also have a non-parametric methods, kernel method, to visualize the change in the conditional in the causal mechanism. So the low-dimensional representation of the change in the conditional distribution. Okay, here you can see application. Basically, we analyze about 90 stocks in NYSE, New York Stock Exchange. We analyze the daily returns, just the daily returns. So the causal relations are basically instantaneous because the resolution of the data is very low, right? Here you can see the relation, the discovered relationship. Furthermore, we can also visualize the change in the mechanism. Actually, this is 2007, this is 2008. 2008, right, is the financial crisis. And actually, you can see we found that this curve is very consistent with the curve of TED spread, head spread. It's a very complex way to calculate the underlying risk in the market. Now, by analyzing only the daily returns, you can recover not only how they influence the other, but also kind of what's driving the change, or driving the change in the causal mechanism, and seem to be related to the market, to the risk in the market. But you can discover this only just from the daily returns. So the 2007, actually the risk is already very high. This is 2008. The risk is very high, it lasted longer, and there was a financial crisis. Of course, we haven't validated everything here, because to do so, we have to really have very rich domain knowledge. But from data mining or machine learning perspective, it's a very nice data set. Quite a lot of relations can be verified. Okay. How many minutes? We have maybe 5 or 3.
Well, we started later, so I think like 7 more minutes.
Okay, wonderful. Let me just finish it within 5 minutes. Thank you. Now we can basically use this approach to do domain adaptation. In domain adaptation, usually we just make some assumptions, and then we can develop methods. We can give some guarantees. But how can we know that the assumptions regarding how the distribution changes hold true in practice? It's better to automatically discover how the distribution changes and make use of it, right? So in this work, basically we consider domain adaptation as a problem of inference on graphical models. You have an augmented graph to represent how the joint distribution can change. And then give this graphical model. In the target domain, you have the values of the features. The problem is nothing but inference of the target variable y given this graphical model, right? So it's a standard problem. According to Pearl, this is the right way to do domain adaptation. So because he's a causal person. So you have to understand why, right? Things are happening, and you have to then you can make use of why. Essentially, the method consists of 3 steps. First, we just learn this augmented graph as a compact representation of the change in the distribution. If there's theta into this guy, it means that for this guy, the conditional distribution, given its parents, can change across domains. That's it. And then, given this graphical representation, we can also learn the prior distribution of the latent variables theta. It denotes the variability, how much this conditional distribution can change across domains. And then in the target domain, we just do inference, right? We try to infer the posterior distribution of the target variable given the values of some other features. That's it. So it's a standard thing. And as you can see from here, basically, I want to make one point clear. When do we really need the causality? For the purpose of domain adaptation, do we really need the causality? Here, actually, I consider this representation as a compact representation of the distribution shift, right? It's not necessarily causal. If you want to go from this representation to causality, you have to make additional assumptions. And here, for the purpose of prediction, we don't need such assumptions. As a consequence, in some cases, the discovered representation can be very different from the causal one. So suppose this is the true causal process. Disease, symptoms, clinic, right? We assign patients to different clinics according to symptoms, right? And then if that's the case, you can see the following thing. Why distribution of X will change? Because if you look at different clinics, the distribution of the symptoms will change. However, the conditional distribution of X given Y is the same. Why? Because Y and S are conditionally independent given X, meaning that the conditional distribution of Y given X is not relevant to how you assign the patient to different clinics. So PY given X is invariant. And this is the representation we can learn from data as a compact one to encode how the distribution can change. For the purpose of prediction, this is sufficient and it's optimal. But if you want to go to causality, usually you have to make further assumptions. In some cases, we assume there are no selection bias, right? And so on. Okay, but for machine learning, that's good since you are not really required to do intervention. It's good. Okay, here you can see the result on simulated data and real data. The message that by automatically discovering the change of the graphical representation and then do inference, the performance is clearly much better. As you can see from the last column, you cannot see it. So right here, you can see the much higher. Why? Because this provides a kind of hierarchical way to do adaptation. First of all, I know the structure is very reliable, right? I can discover the structure, the graphical representation is very reliable. And then I try to see how each of them changes over time across domains. So this way, you do not really make very strong assumptions. You learn that from data, you make use of it. It's adaptive. That's why you can see accuracy is much higher than alternative methods. Okay, then the last thing I want to briefly mention is another way of doing domain adaptation, still by making use of the learned representation. This is a setting of nonlinear ICA, nonlinear independent component analysis. We observe variables x1, 2, 3. They are nonlinear transformations of independent variables z1, z2, z3, and so on. And we want to recover the latent variables. Generally speaking, the solutions to nonlinear ICA are highly non-unique because after non-trivial nonlinear transformations, independent variables can still be independent, right? So that's why solutions are highly non-unique. Recently, basically in light of Apple and others, it has been reported that if you assume that only the distribution of the independent variables change across domains in some way, then the whole transformation G can be recovered. So you can recover the independent variables without difficulty. What that means, essentially, you can also consider this result as an instantiation of minimal changes. You only allow those hidden variables, latent variables, to generate the measured variables to change independently across domains. And then you can show that for any wrong transformation, the latent variables will change dependently. They'll be influenced by multiple kind of hidden factors. So this one actually enforces minimal changes. Then you only allow changes here. G is shared across domains. This part is invariant. That's why you can recover the latent variables and the function G. Okay. We went further. Essentially, we did a partial disentanglement and said the following thing. In order to explain how the distribution changes, so let's consider image data sets, right, across different conditions. A lot of hidden factors are the same, right? A lot of hidden factors are, but G, this part will be the same. They are shared across different data sets. Some factors can be different. They have different distributions, but the mechanism or the mapping to generate the images from those hidden variables would be the same, right? How we generate the images would be the same, as long as you have a specific setting and specific set of concepts, right, to generate the image. And then we show that in this case, we can recover the changing factors uniquely, and we can recover the subspace of the invariant part. Given that we can immediately have the identifiability of the joint distribution in the target domain, and then you can do domain adaptation. It's very interesting because in many cases, only few factors actually change across domains. Now you can locate those factors and make use of their changes and do adaptation. Okay, so I will skip the result. Yeah, summary. So as a summary, you can see a number of machine learning problems are really related to causality, or some kind of weak notion of causality. When you make decisions, you care about the causal effects. And actually, from the, we are AI researchers, right? Whenever you deploy any AI system, you have to care about the causality because AI system and human society will influence each other in some way. So we have to care about the long-term causal effect. When we do domain adaptation, right, reinforcement learning, recommended systems, we care about the causality, and you can also think of trustworthy AI and explainable AI and fairness from a causal perspective. So causality seems to be at least conceptually, causality should be a very, very important problem. And then I hope that you agree that causality is not mysterious. From data on the very mild assumptions, you can recover causality and representation. And we can make use of this kind of representation to solve a lot of problems. Here I use the word pseudo because under those assumptions is causality. Otherwise, at least you can consider it as a compact representation of the distribution change, right? You can still enjoy the benefits. And why? Because in many situations, you don't really care about interventions. You don't want to change anything. You want to just make adaptive prediction. So causality can be recovered under appropriate assumptions. And of course, right now, there are so many open problems, right? We want to learn things from images and from text, video, and so on. So for each of them, we really have to find the specific conditions that are plausible, right? And kind of plausible in reality. And furthermore, we have to make sure that those conditions are strong enough or informative enough so that we can recover the underlying representation uniquely. Okay, thank you very much.
Thank you. These questions. There were already some during the talk, but probably
Technical.
please go.
One is so when we to do all these things to kind of decide which pair of variables is conditionally independent or not. So in theory, so the condition depends not like a binary state, so it's either dependent or not. But in practice, we have this finite sample of data, and we can measure maybe some metric of dependence, but it's like a number. It may be very small, but non-zero. So how do you in practice? So there is some threshold or what?
Wonderful. That's a wonderful question. So here, for simplicity, I only mentioned a constraint-based method, right? And by constraint, I mean condition independent constraints. You are totally right. So even in constraint-based method, you have to determine the say, significant level, right? The significant level for the test. So that's something you just mentioned, right? Would you like to use 0.01, 0.05, or 0.001? It really depends on sample size and lots of other factors. And furthermore, you actually made a very good point in the following sense. In many cases, it's really hard to say, oh, we have a kind of, we can make a binary decision. And those independent testing results are not independent. They're coupled, right? Because if they are independent given this guy, there should be independent given, say, this guy together with another guy. Those tests are not independent. But in this method, in PC, you assume that those testing, the tests, conditional tests are independent. So that's a problem. As a consequence, you can develop some score, right? To consider all variables at the same time. So it's known as a score-based method. And clearly you have to find the threshold. In score-based method, usually you can use the BIC score or some other score, or even kind of cross-validation, right? To determine the threshold or to see whether you have the edge in between. Is that answer to your question?
Yeah, I did the second part.
Basically, to summarize, you're totally right. You have to find the threshold, right? And a lot in the past 10 years, a lot of people try to deal with this problem. They try to improve the efficiency, statistical efficiency, by using different ways to kind of determine the threshold, or by controlling something like a false discovery rate and so on. So it's a kind of hot research direction, and it's a very sensible question. And a lot of research is still going on in this direction.
So what is research like that works in robustness? In the sense that, in your last slide, you were talking about that, determining the absence of variations or causality integers. But if the solution is degenerate, you don't
solution is the
degenerate.
Degenerate by that you mean?
Like your model is just giving like a degenerate solution, and real like the prediction they don't correspond to what's detection or whatever you're doing. So causality wouldn't make sense in this specific case. So how the causality and how the variables that interact with each other connect to the robustness of the solution itself.
Okay. So basically the question is how the causal represent or causality, right, is connected to say robustness of say prediction. Yeah. Okay. First of all, very good one. What's your definition of robustness? There could be multiple definitions.
Yeah, so robustness, the way I see it is standard deviation around is like small around the energy of the model.
Yeah.
Which means if we are back, we don't deviate a lot from the element.
Yeah. Okay. So now, given your definition, let's go back to this representation. Remember, in this representation, we can see whether conditional distribution changes, right? So suppose for y, you can see this part is invariant, right? This part may change. So now the problem is, if they change quite a lot, I can make use of only this part for prediction. It's very robust because this part is always the case. It can be used for prediction y, right? And the model, no matter how the causal relations change, or no matter how how different domains are, I don't care because this part is invariant. This is one way to achieve robustness. You want to make use of invariant causal influences for robust prediction, or for conservative and robust prediction. By conservative, I mean, in principle, you can still make use of those modules with changing distributions adaptively, right? It's always informative, but you don't want to be kind of so sensitive to the changes. That's why it's conservative and robust. Is that answer to your question? Great.
Just like okay.
Yeah. So for example, so to decide so where we have this independence between some pair of variables, we do it like conditional. For example, you want to understand whether x and y are independent conditional z, right? But for example, but if z is some not continuous but discrete variables with a small number of states, it is we can do it because like we have for each value of z we have many samples.
You're right.
But if z is continuous, how do we do it?
One of that's a kind of technical, second technical question. So it's about the conditional independent test, right? So if you want to see whether x and y are conditionally independent given z, right, given or z, and if z is discrete with very kind of a very low cardinality, then it's very simple because for each value of z, you can test for independence. The problem, I think, hardly the problem is in a situation where you have a lot of discrete variables in a conditional set or a conditional variable, right? Discrete conditional variable with very high cardinality. Then you have to make use of a lot of data points in order to have non-trivial conclusion, right? That's completely true. In a continuous case, however, usually it's simpler. Technically harder, but it's simpler because you can make use of neighboring information. You can make, something, if you assume smoothness, then you can immediately make use of neighboring information, right? To gain kind of higher power of the test. So actually, this is the idea underlying our kind of kernel-based conditional independent test. I think it was given here. Yeah, so we have a kernel-based conditional test. Essentially, that's the idea. It could be very powerful if the distribution is smooth. Is that answer to your question? Okay, wonderful.
Yeah, I have probably, I don't know if anyone has more questions. I have one question, which is probably a bit provocative. So, machine learners, they like to develop algorithms and then they need to show that these algorithms work. And I know pretty well that in some areas, it's not that easy to find the proper data sets to show that your particular ideas work well or not. In your case, in your area, are you have a lot of data and very easy for you to show, or you more really all the time looking for a suitable type of data to show the relevance of your ideas and so on?
That's a wonderful question. So actually, that's still a problem. You're totally right, right? In machine learning, you can see the developments were heavily driven by the kind of benchmark datasets. UCI datasets are popular use, and then once I have the method, I can immediately run the method on the dataset and report the result. If it's good, then it's easy for the paper to be recognized. So in causality, that's a problem, and I have encouraged some kind of biologists to produce some benchmark datasets, and a lot of people actually are trying hard to produce these kind of datasets. So I would say, in several years, we have a collection of benchmark datasets, real datasets, and people are producing more. And in several years, I believe we are going to have a kind of rather rich set of benchmark datasets to evaluate the performance of different causal discovery methods. So wonderful question, and it's basically you can see people are doing that.
Okay, thank you very much. So I suggest we thank Kun for a very nice talk.
Thank you very much. Thank you.